Welcome to this lecture series in linear algebra. We are starting a new module and we will be discussing general structure theory. We have done some structure theory before, even though we did not use this phraseology. So all these decomposition theorems, like primary decomposition theorem is a general structure theory statement. So we will be discussing structural results, and our first goal from now on is to prove the Cayley-Hamilton theorem. And we will take our time to get there. And then we want to discuss determinants. So that is the aim or goal from now on, or rather the course content from now on. And I also consider this slightly more advanced than what we have seen so far. So anyway, let's continue. So we will not be talking about inner products now. If we want to use anything about inner products, we will mention it. But now we are back to general setting. The field is not real or complex necessarily, just any arbitrary field. Okay, so what we need to know is what are eigenvalues, what are eigenvectors, and we need to know what is the minimal polynomial of a linear endomorphism, the primary decomposition theorem, etc. So I'm not going to recall any of this in detail because we have done it so many times, and you can always go back to the corresponding videos. One thing that we will need for this lecture is Euclid's theorem for polynomials, and this is the statement. Again, we have used this so many times that there is no point recalling it, or rather, there is no point reading this out. So let's continue. So we will define what is an eigenpolynomial. So fix an endomorphism on a vector space V, and the base field is denoted by F. So an irreducible polynomial over the base field is called an eigenpolynomial. Just like we had eigenvalue, this time we are talking about eigenpolynomial of T if kernel of Pt is non-trivial. So obviously this means that there is a non-zero vector which is killed by Pt. So irreducible is important here. An irreducible polynomial is called an eigenpolynomial of T if it has a non-trivial kernel. Well, I shouldn't say the polynomial has non-trivial kernel. I mean the corresponding endomorphism has a non-trivial kernel. So one thing I want to emphasize is that this is non-standard. This terminology is not standard. So if you're going to use this terminology to someone who has not seen these videos or has forgotten even if he has seen these videos, then you might have to define it for them. What do you mean by this? This is not in any textbook. I invented this terminology just for my purpose. And I think it's a good terminology, which I will justify a little bit. So note that lambda in F, I have written T, lambda in F is an eigenvalue of T if and only if x minus lambda is an eigenpolynomial. Right, this is a immediate consequence of the definition. And so this basically eigenpolynomial generalizes the notion of an eigenvalue. That's all. So yeah, I should add monic. I don't want just an irreducible polynomial. I want an irreducible monic polynomial. Sorry about not mentioning this first. An irreducible monic polynomial, because otherwise you would pick an eigenpolynomial and scale it and call it another eigenpolynomial. We don't want to do that. Okay, so an irreducible monic polynomial over the base field is called an eigenpolynomial of the endomorphism if the corresponding endomorphism has non-trivial kernel. And this generalizes the notion of an eigenvalue via this pink statement. Okay. So let's see an example. It's a somewhat lazy example, but it is what it is. So fix or define an endomorphism of R3. The base field is R. When we define an endomorphism of R3 via this equation where E1, E2 and E3 are the standard basis vectors. So this is E1, or maybe this let's call E1. So this is E1, that is E2, and the third one is E3. This is E3. So these are three standard basis vectors of R3, and this is how the endomorphism behaves. So if you think about it, all it is doing is it is rotating the space around this, about this axis by 90 degrees. So every point on this axis stays put, and the entire three-dimensional space is rotating by 90 degrees under the influence of t. Okay, so just note that x square plus 1, which is obviously a monic polynomial, is an eigenpolynomial. Right? Why is that? First of all, it is irreducible over the real numbers, and it is monic, obviously. Why is it an eigenpolynomial? Simply because, just calculate, if you calculate t square plus 1 and the action of it on E1, you get 0. So it has a non-trivial kernel, and therefore it is an eigenpolynomial, right? The example which I really would have liked to write down here is rotating by some other axis. This is like the most boring axis to rotate about. If you rotate about some other axis, you would again get a 2-degree eigenpolynomial. But it was just getting, calculating all that was getting little bit tedious. One could do it. So you choose your axis, whichever you like, and rotate by whatever angle you like, not 360 degree, but because that's not rotation at all. Some non-trivial angle, and then you will again find the same thing, but the polynomial will look different, but essentially the same thing. Okay, so my point is that eigenpolynomials are strictly more general than eigenvalues. Given an eigenvalue, you can create an eigenpolynomial, but since there are eigenpolynomials of degree higher than 1 in general, like we see in this example, they capture a little bit more than what eigenvalues capture. Okay, so this is an example, but here is a full characterization of eigenpolynomials. Fix an endomorphism on the vector space. Then something here is an eigenpolynomial of t, if and only if. So maybe, again I should say monic. So if and only if it is monic, and Px is an irreducible factor of the minimal polynomial of t. Right? So you take the minimal polynomial of t, you find a monic irreducible polynomial, that will be an eigenpolynomial, and every eigenpolynomial occurs this way. So if you can find minimal polynomials of any given endomorphism, then you can find all the eigenpolynomials in principle, because factorizing a polynomial into irreducible components is not a simple task. So anyway, let's prove this. So first, suppose that Px is an eigenpolynomial. Right? So we assume Px is an eigenpolynomial of t. We want to show that Px is an irreducible factor of the minimal polynomial. So let mx be the minimal polynomial of t. And assume on the contrary that Px does not divide mx. We want to get to a contradiction. But now, since this is an irreducible polynomial, this assumption means that these two polynomials are relatively prime. So thus Px and mx are relatively prime. And therefore, by Euclid's theorem, by what we recalled in the beginning, we have, or rather there exist, polynomials in the base field, and the base field is denoted by f. I have not written it, but that is what that is the notation that we will use. There exist ax and bx in the over the base field such that this is equal to 1. And therefore, this is the identity operator. But since m is the minimal polynomial, this is 0. So we can just erase this. Okay. And now since p, or rather px, was an eigenpolynomial of t, there is a non-zero vector which pt kills. So with that, and if we call this star, what we get is, right, we just operate this on v and that on v, and those two things must be equal. But this is 0, and hence this is 0, but that means this is 0, and that's a contradiction to the fact that v is non-zero. So this implies 0 is v, and that's a contradiction. So this finishes this part of the proof. Our assumption that, let me maybe change the color. So our assumption that px does not divide mx is wrong, and therefore we are done. Yeah. So this direction is fine. Now let's do the converse. So let, again, mx be the minimal polynomial. We have already written it, but no harm in writing it again. And let px be a monic irreducible factor of mx. So we want to show that px is an eigenpolynomial. Right? So suppose not. So then kernel pt is trivial, which implies pt is invertible. pt is an isomorphism. All right. And now say mx is equal to that where p1x up to prx are irreducible polynomials. And of course, each ki is at least 1. So just take the factorization of mx in terms of its irreducible powers. I mean, just take the, what should I, the factorization of mx into its irreducible factors. P1 appears k1 times, pr appears kr times, and p appears k times. We already assumed that px divides mx, so there is some non-trivial power of px that appears as a factor of mx. K could be 1, but it is at least 1. So suppose we have that, then by the primary decomposition theorem, we know that V, the vector space, is the direct sum of these things. But what is this? Well, since this is an isomorphism, every power of this is also an isomorphism. Therefore, this is an isomorphism, and hence this is the trivial subspace. So this is same as, the trivial subspace direct sum the remaining things. So the vector space V is just the direct sum of the remaining things. Right? But this implies that kernel of sorry, what have I written? Kernel of P1x to the power k1 dot 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 Prx to the power kr is the entire vector space. Sorry, this is a T. Apologies. This is a T, which implies mx is not the minimal polynomial. Why is that? Because just consider this polynomial p1x to the k1 prx to the power kr. So if you consider the corresponding endomorphism, that annihilates the entire vector space, and hence the degree of the minimal polynomial should be at most the degree of this. But the degree of the minimal polynomial is more than the degree of that. And that's a contradiction. So this contradicts the fact that mx was the minimal polynomial, and hence we get the required contradiction. We assumed something, but that assumption must be wrong. So that finishes this proof, and with this I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.